I want to start looking at derivatives of our trigonometric functions. Okay. And we should realize by now that we can take derivatives of any function, right? Because what does the derivative actually tell me again?
The gradient function.
It tells me how the gradient is changing over time. And let's just look at this graphically, right? We can actually get an idea of what this would look like, right? Let's have a look at the gradient for this part here. What gradient do I have here?
Positive.
Positive. So it's positive, positive, until I get to about where?
One stationary.
Yeah, this is actually pi on 2, and what would the gradient be at that point?
0.
Okay. And then I can go negative, negative, negative. Where's the next place at 0?
0.
Here?
At the
Minus
trough.
1.
Right here. I want to say that's 3 pi on 2.
Yeah, it would be.
Yeah, that's right. 3 pi on 2. It's 0 then what happens afterwards?
Positive, positive, positive.
Yeah, okay. So we can actually get an idea of what this is going to look like. Now, just as a reminder, when my gradient is positive, right, this is y equals the sine of x. When my gradient is positive, what will y dash be? What will the derivative be? What does it mean for the gradient to be positive? What does that mean? Okay, so it should be above the x-axis somewhere. What does it mean when it hits 0?
It's on the axis.
So it should cross through this at some point, right? And then you notice here, even though this part here, even though I have some part above the axis, remember you're looking at what the gradient is doing. So in this case, it's negative all the way down. Yeah, it'd be all the way under. And then what's going to happen here?
It'll be 0.
Yep.
It'll cross again.
And then it's going to be positive
Above
again.
the x-axis.
Yeah, and it turns out, if you actually try and find the derivative of this,
Shift it over a bit.
it looks something very interesting. So remember, I've got an idea of what I expect it to look like. It should cross through these 2 points here.
How are you doing that?
Wouldn't it be the same thing?
If I do f dash of x,
What
what do you get here?
A cos graph.
Yeah, that's exactly right.
What?
Can you see that, right? It's positive all the way until this point.
and-
So it's negative all the way down. And then I go back up into the positive components, right?
What's double dash?
But I want to, before that, I want to make a note of this, right? So I've got my derivative of sine of f of x. It looks like cos of f of x, and it is. But I want to make a note here. Because we don't just look at our standard forms, right? We don't just look at our standard forms, sine of x. What can we do to them? How have we learned about how I can change sine of x to graph? What things can I change? I can change the amplitude, right? Yeah, that's pretty straightforward. If I have something like this, how will that affect the derivative? Well, if I zoom out now, what's happened to my
Both
graph?
has gotten more.
Yeah, why is that? Well, if you, yeah, why does the amplitude stay the same? Well, if you think about it, this is just a constant on the outside.
The function is the sine x.
If it's just a constant on the outside, if you took the derivative, just like with any other constant, when you take the derivative of like 5 of x, it just becomes 5. So if you take the derivative of this, that would just become 5 cos of x, right?
Yep.
Does that make sense? So in the same sense that when you take y equals to 5 of x and you take the derivative there, that constant, that's not going to affect it at all.
5.
Yeah, it would just equal to 5, the constant stays there, right? In the same sense here, I can take the derivative of sine f of x, or sine of x in this case. If you took the derivative, the constant would just stay there, and you get cos
Yeah,
of
the thing
x.
that's like stumping me is the fact that it just goes to 5 cos of x.
Yeah, well, we saw that here
Yeah.
using a graphical method, right?
See.
But I want to highlight what happens when I have something on the inside. Let's say I had sine of 5 of x there, okay? So let's say I had sine of 5 of x.
Oh wow.
And the green one is the derivative. Why is that? Well, what have we actually done here? Y dash is actually, in this case, equal to 5 cos of 5x, okay? So you remember, when I have a coefficient inside that x there, it changes the period, how frequent it is, right? But, right, you notice that the amplitude of the derivative is much higher, isn't it? Why is that? It's because they've actually applied chain rule in this case. Because if you remember, sine is just a function. Sine is just a function. So we have to be careful when I'm looking at the derivatives here. What you actually have to do is, if you have sine of f of x, you have to take the derivative of the inside and put it outside cos of the original graph, right? So let me just reiterate. If I have sine of 5 of x, that actually becomes 5 sine of 5 of x, because what's the derivative of 5 of x? It's just 5, right? And so that comes out there. So you can see how if I have something inside that bracket there, that's going to actually affect the amplitude of the derivative. And we can actually look at what's going to happen with cos as well. It's going to be a very similar idea. So if I have the original graph of cos of x, let's just look at the gradient function too, how it's changing. So cos of x here, I'll zoom in. So here I've got all negatives until here, which comes 0, and then positive all the way. And then I guess you have 0 again here, right? If I take the derivative,
Negative sine of it.
let's see what we get. What does this look like? So it's
Negative sine,
below the
negative
axis,
sine x.
0,
Negative sine
and above
x.
it. Yeah, it looks a lot like the sine graph, which your sine graph normally looks like this, but can you see how you've just got the negative version of it? It's literally just flipped in the x-axis. So the blue line is your original sine graph, and if you flip it, you get that black line
It's
there,
like second stuff.
which is negative sine of x. Can you guys see that?
Yeah.
Right? So I actually get negative sine of f of x. But remember, again, cos is also just another function. So if I change what's on the inside, right? If I change what's on the inside, what do you notice with the amplitude of the derivative again?
Changes.
Yeah, the derivative, I'll make it a bit smaller so you can actually see it, right?
Yeah.
This red line is your original function. That orange line is your derivative. You can see how I've changed the period, affected the period on the inside, affected the period on the inside, and what's happened to the amplitude of your
It's
derivative?
got larger.
It's gotten much larger. So in this case, what's happened? Well, if I had y equals
You
to,
just differentiate and put it out the front, don't you?
yeah, cos of 2 of x,
2 cos 2x.
y dash would be equal to, well, what's the derivative of 2 of x?
Negative 2 sine 2x.
Okay, derivative of 2x is just 2. I've only done these examples just like rudimentarily because I want to show you that the period of the original graph affects the amplitude of the derivative. Can you guys see that? Yeah. Does that make sense? Yeah. Okay. Any questions about that? Right. Why do I care about this? Well, I want to look at the derivatives of a whole heap of different functions. Now, I've just got some basic ones over
How
here
come you haven't done tan yet?
because I'm going to get to tan in a second. We can actually do it ourselves.